Yep. Okay, this is chapter 16 in your book. We're going to start covering linked list, which is going to be your first data structure besides your array. So far, we've talked about elements that are contiguous or sequential. Linked list, we're going to talk about the first data structure where it's a linked data structure, aka you have a piece of data and you somehow point to other pieces of data. And this is going to give us some advantages over array, but in a linked list, you're going to find that an array still has a couple advantages over a linked list. Right, we're going to learn. Thanks. Okay. Problem with the array size is fixed. That, if you look at the board, gives you a problem with push front or remove front, but more importantly, push back may be O of n if you have to recopy all the pieces of data. So that's actually a pretty significant error. They talked about sorted and unsorted arrays. Did y'all do that in procedural? No, that's fine. That's perfectly fine. We'll get to that later. A linked list is going to be a little different. You're going to have, it's going to be a collection of items, and we're going to call these items are going to be contained in something we call a node. I'm going to use that word node a lot, so start getting used to it, because it's not just for a linked list. There's nodes and everything else. It contains two components, the data and the address or link of the next node in the list. Hey, what does that second one sound like? A pointer. Yep. So I'm going to go back to my little picture. Ooh, let's see if we can. Oh, okay. So I have all this space over here. Beautiful. Give me a number.
7.
7. So we might have 7, and then we're going to have a pointer to something else. What do you think that pointer is going to point to? The next element. Okay, great. Give me another number. 8. Oh wow, we're so original. We'll have this go over here. 27, yeah. And we're going to say this is the end by putting a 0 because that pointer goes to null, and by convention that's where the kernel of your operating system is, so you shouldn't be writing to that anyways. So if you ever have a pointer going to 0, aka null, stop. All right. How many elements are in this linked list? 3. Okay, perfect. Now, when we create a linked list class, we're going to need to know the head pointer. So the head pointer is going to point to where we start. So back up here with our picture, we have head. And I'm going to be a little more precise here and call it mhead. So you realize that it is a member variable. I'll make that a capital H. And that points to the first element of the linked list. So in this one, how many elements are in this linked list? Yeah, the first one, the one up top. 4. There are 4 elements in this linked list because there's 4 integers. And even though there's 5 pointers, there's only 4 integers, and that's how many are in it. This picture down here is just to give you some memory addresses. Remember, head is a pointer, so if it held 1200, and that's where your first node was, at address 1200, that's where the 45 would be. And then next to that 45 is the address of the next element here, 1575. It jumps over to that piece of memory, which contains 65, and then that could be another pointer. Do you understand what's going on in memory? Do your addresses need to be ascending? No. They can be in any order they want. You can have it jump all around memory. That's perfectly fine. All right, node declared in a class or a struct. They use a struct here. Let's go and jump over to some class code and make our own little linked list.
How would you delete?
We will get to that. Did y'all do linked list in Java, or is this?
We should have.
No, you may not have. You may, which is fine.
We were going to, and then we never did.
Oh, okay, great. All right. I'm going to call it the singly linked list, and you'll understand later why I'm calling it a singly linked list. But we're going to stick with that for now. Include IO stream. Wait, is this too dark for the people back there? Nope. All right, great. Kind of. All right, 1 second. Let me go ahead and type that out. Let me increase my font. Now it's, this one is just right. How's that?
That was good.
All right. Return 0. All right, so we're going to class, I'm going to call it a singly linked list node. And make a little comment because SL node may be confusing, so that's why you say S node equals singly linked list node. Because no one wants to write singly linked list node every time they use this. Public. So what is it containing? A what? So the node is representing this thing right here. So what is it containing? A value and the pointer. All right, let's do the pointer first. What's the pointer pointing to?
The next address.
The next, not an address, but it's pointing to a
Next element.
a what? It's pointing to a, I'm sorry, I couldn't hear you.
What? Yeah, the memory of the next element.
Next, not the next element, but the next
Node.
node. Right. So I literally type S. And that's okay. Why is this okay? Some people think that this may perform an infinite loop. But is it? Why is it not performing an infinite loop? Yeah, what it calls, what was that?
You don't call it.
Right, you don't call the constructor. If I did this, bad things would happen. But that, I have it as a pointer, so we're okay. Is everyone clear or kind of understand what's going on there? Because
We use SL node in front of the pointer.
that's what the pointer is pointing to. It's pointing to another singly linked list node.
So does it know how does it know what's in the linked list?
Because we're defining it right here.
Okay.
And it contains a pointer. Yes, so say?
That line right there.
Yeah.
Where you are right now.
Yes.
It just moves to the next element. Or
I don't know why I made this public again. Y'all gotta stop me with this. All right, here we go. Let's start. Let's do this. And actually, let's make. And if we wanted to, well, we'll go ahead and do it this way. Equals new. All right. Let me make sure I typed that all correctly. It's always a good thing to test.
Why is it bad if that's not a pointer?
Anyone? Yeah.
It's gonna keep creating an object. Yeah. If you create an object by creating this object, it will just keep going forever.
I don't understand why.
I won't even let you do it.
Declare the object. There's a default of this sort of constructor that it calls, and so when you say it's not a pointer, it makes the object itself. It tries making the object, but within the object, when you create it, it also has to make another object, and so it keeps going back and trying to make a new object, and you can never break out. You can never finish the object.
Why does it not? I don't understand why it doesn't finish the objects. Like, so is the pointer is pointing to what?
Okay, well here you go. If I'm me and I say part of me is me,
Okay.
but in order to make me, I have to make another me. It doesn't make sense because it can't exist. If I say I'm two of me,
Yeah.
how, is that possible?
You can't do it yourself.
You can't be two of yourself. What?
Unless you're zero.
Nice. Well played. Yeah. Well played. I can't be two of myself. Because if I was, then I would just keep creating myself over and over again ad infinitum. And it doesn't make any sense.
So
That's what this node is doing.
Pointer do?
Well, the pointer, instead, the pointer's saying, what I am, I have myself, and I'm able to point to another copy of me.
It's not exactly
Okay.
So I could point to myself, and now I'm completely legal. Or if I was able to somehow clone myself, I could point to the other me. But that's all this pointer's doing is I'm saying I point to something else that's me. Yes.
Alright, so is that like
Actually,
I guess I'm kinda lost because like is that like a predefined
Index is a variable. So I'm saying the SLL node is going to contain a variable named indexed. Its type is a pointer to an SLL node. So you know how with other objects you made a car object, it might have an engine element and a chassis element. This is an SLL node, it has an indexed element or member variable.
Why is a linked list better than just a regular list? This seems more confusing.
What's a regular list?
It's just, isn't it? Well, why not just do a array or vector than a linked list?
We're getting there.
Okay.
First, we need to understand this data structure before we can do an analysis, which I started on the board. All right, so we have a pointer that will point to the next node. What else needs to be in this node? The type. What's the type? Well, we could make it an int. I'll do mval. But what else could we do here?
Could do a template.
Yeah. Aha. Make a linked list of integers. There we go. So now we only have to write this once and never again. Okay. Hey, look at Rand.
Now you can type what all at once.
Yeah.
Well, here it's integers. I could put in doubles, floats, another class, strings. I could even make it a singly linked list of singly linked lists if I really wanted
So
to.
what is, by doing a template, what are we saving ourselves?
If we, by making a template, notice beforehand I'd have to put the type of mval to be int. So if I wanted to do one for doubles, I'd have to copy and paste that code. If I wanted to do one for strings, I'd have to copy and paste the code. By making it templated, I'm parameterizing its type, thereby I only have to write it once for any type that's being used inside the singly linked list. How about that for a speech?
Yeah.
Sounds great. All right, good. We have a node. All right, beautiful. Let's make sure it looks right. Yep. Okay, let's look at a couple more. Okay, they're going to use .info and link. I'm using .mval for info and .mnext for link. It's the same thing. I think the author's idea here is not the best programming practice. So we differ of opinion. That's okay. Okay, so if we create head dash,
What are you using for info?
that mval. Hey, let's go ahead and create a constructor. How about that? You all like constructors, I hope. So it's going to be past the val, and we'll go ahead and give it what's next, right? Oops. Let's do this the right way. Tab new. List.cpp. Whoops, that was. Oh, this is a CPP. Okay. I have arranged this incorrectly. Womp, womp, womp. All right. Header file. Boom. If not defined, go ahead and define it. Go out to the end if. There we go. And now, ooh, I didn't put that over there. That's bad. There we go. Now we can include up top. All right, now if we combine, nope, didn't like that. Yes. Cool, this is gonna be bad. Good, we got that. So Now we need to move main to a separate main. So this will look more like your labs.
So why do you have to do that?
Because you're,
Why do we have to do that? That's a lot of questions. Right, and now we don't have the constructor declared, so let me go ahead and comment this out for the time being, just to make sure it compiles. Yeah, there we go. Why do we have to do it? This is how you split it up in C++. We went, go ahead and review last class about why this has to be split this way. Okay, so now I have it split. Here's the header file. Here's the CPP file. We don't have any implementation yet. And here's the main CPP, which just has main for us. Yes?
does there need to be a header file, or that's just good practice?
It's good practice. Just like you could write everything inside of main and not use functions. Don't do that. But it's good practice to do it this way.
Okay.
All right, so include the linked list, great. Now let's go ahead and use a constructor. So we're gonna go ahead and implement the constructor. Oh, the little c. And what do we call it? SL node of t. And then how do we put this together? Well, mval equals val, and then we'll have mnext equals next. Simply copy it over. Does seem like a lot of work. That is true.
Is a vector faster than most methods?
The vector already has this code written for you
Yeah.
for an array. And they have, in STL, they have something called list, which is the singly linked, actually the doubly linked list implementation. So they've written all this for you already. They still had to write this, but they have it written for you so you don't have to write it again.
Okay.
We need to implement it so you can prove to me that you understand how the data structure works. All right, let me make sure that code compiles before I say, hey, what does it do? Redefinition, that's cute. Oh, yeah, because we don't put in the CPP anymore, we just compile main. Boom, all right. So what does this line of code do? Keeping in mind, well, yeah, what does this line of code do?
Just a value of 10 and then pointing to null, so I guess ends just point out.
Right, so we have head, we create a node templated on an integer. We call the constructor passing in 10, which sets the value to 10, and then we also pass in null, which sets mnext to null. So let's go ahead and draw that up on the screen. Hey, it went black. Okay, there it goes. My screen went black. So what that's doing up here, first thing it does, creates the node for us. What was it put in the data?
10.
10, all right, just make sure you're paying attention. And then the pointer is going to,
No.
okay. I think we understand the code pretty well. So actually, let's do one more thing.
So it's size 10, like 11 at the same time, there's a null value?
Oh, what's the size of the linked list?
Yeah.
What is the size? How many elements are in it?
Whatever you, I guess, for like, I guess.
There's one element right now, so the size is 1. But maybe you're asking me how much memory it's taking up?
So memory would be 2.
Memory would be, well, it's the size of an integer plus the size of a pointer. The size of a pointer on my machine is 64 bits, aka 8 bytes. The size of an integer on my machine is 4 bytes. So the total size of this SL node is 12 bytes. Did y'all do size of? No, okay, well it's head, oh, I gotta break the, actually no, that's private. Let's do the size of real quick. Size of int, because this is actually, did y'all do size of? If y'all didn't, we should go over it real quick. Nope, okay, size of an integer, size of int. That is a built-in function to C and C++. Size of a float. Size of an integer pointer.
How's that?
And we'll do size of a, we'll do a double. And what's the last one we went? Long. We want to do long. And then we'll also do size of an SLL node, because you can also call it on your class. Okay, let's compile and run. Didn't like one of it.
Didn't like SL.
SLL node. Oh. Of an integer. There we go. Okay. Oh, 16, which is not surprising. So size of an integer is 4 on my machine. These numbers are machine dependent. I will say that these are the common numbers that you'll get when you run, but keep in mind that this is not necessarily always the case. If you're on an embedded chip, your phone, these numbers are going to be different. But on my machine, they are these numbers. An integer is 32 bits, aka 4 bytes. Size of returns the number of bytes that something consumes in memory. Integer is 4, a float is 4. Note a pointer, an int pointer, is 8. All pointers are going to be the same size. Whether it's an integer pointer, a void pointer, a double pointer, an SLL node pointer, they're all the same. A double is 8, a long is 8. And then saying an SLL node is 16, probably because it just allocated 16 and there's 4 extra free bytes that it's just not messing with, which is fine. Y'all see what that's doing? Yes. Maybe. All right. Good old side comment. All right, putting it together. Using this object, you have your head. We're saying address 2000 up to here. Dot info is 17, so head dash info or mdata is 17. Head dash link, this guy. Dash info again, so you go from head to the link to dot data or info where you get the 92. Do you see how you can kind of link down to get every element? Yes.
So will we be adding an insert method, or are we just going to do an add at the beginning or add at the end? Because I know, at least with doubly linked lists, you can insert double.
We'll be doing all of it. We'll be doing all of it. Okay. Let me stop here. We're going to